Good morning, everyone. Question?
Yes, for the share of flow, what is AR?
AR is the reduced area based on the minimum diameter DR, right? So this would be when the shear plane is going through the threaded section. And this, by the way, could be quite common, right? By the time we look at the adequate bolt length and we look to find the unthreaded lengths, we can find that the shear plane is going to be going through the threads. So we have to use the reduced area, which in return is going to reduce the ability of the bolt to handle a shear force. Right? And this was clear in the example that we did last Tuesday when we looked at the shear of the bolt. This is the example we did. We had the tau is equal to V over A, and this was a case of a double shear, so I had to use F over 2, and then it was going through 2 bolts. But the part I want to emphasize here is when I use the nominal area, which was 3/4 of an inch, the force that the connection was able to handle came out to be 57.8. If the bolt threads extend into the shear plane, then I'm using AR. And when I use AR, this gets reduced from 57.8 to 45.9. So if I have a choice, I would try to make sure that the shear plane does not go through the threads. But if you're using standard bolts, you know that you have this unthreaded length that we can find out easily based on the bolt height. And yes, and sometimes it is going to be going through the threads. Does that answer your question? Okay, very good. All right, so today is the really the last class that we're going to be learning new material. And we have an easy one, continuation of what we started last week. So, I'm sorry, this week earlier. So on Tuesday, we learn about bolted joints or connections that are subject to a shear force. And specifically, this shear force was going through the centroid of the fasteners. So, for example, when we look at two plates that are fastened together, and if I look at a front view, I would be looking at if I'm looking from this side, I will see this. And I would see the array of the fasteners like this. So if these two plates are subject to a force like this, when they are spliced, we're trying to shear through the bolts. So this force is applied like this. this is how my fasteners are aligned. And if I look at these fasteners, I can clearly see that there is a line of symmetry here, and there is another line of symmetry here. And we can see that, oh, the centroid of these fasteners must be somewhere here. But the point that is important is if the force is going through a line of symmetry, is treated as a concentric compared to the array of the fastener. So what I'm looking right here is a shear joint with concentric force. So the force has a line of action that pass along a line of symmetry of the fasteners. And when we looked at this type of connection, we said we are going to consider possible failure modes. And the things we checked for were like the shear of the fasteners, and this is when we looked at the shear of the fasteners, we have to consider whether the shear is going through the threaded or unthreaded portion, which relates to the question that was asked earlier. If I'm going through the threaded, I'm using AR or DR. And if I'm going through the unthreaded, then I simply use the nominal diameter D. We also checked for the tensile failure of the members that are connected. We then checked for the bearing stress. And also when we looked at the bearing stress, we look at whichever is weaker, the members or the fasteners themselves. Of course, if they're both made of the same material, have the same bearing strength, then they will be equally good because the area, the bearing area is the same. One is pushing upon the other. And finally, we looked at the shear tear out. So this is briefly what we did last Tuesday. So today I would like to move forward to shear joints with eccentric loading. So the loading is considered eccentric is when the load does not pass along the line of symmetry of the fasteners. So what does that mean? I could be looking at a connection where I have this horizontal member attached to some vertical member like this that is fixed. And then I have an array. So this member, of course, would extend here like this. You just cannot see. And this is fastened. These members are fastened together by an array of fasteners, maybe something like this. So when we look at these fasteners, we can consider, or we can easily find the centroid because we have lines of symmetry that we can construct. So if I want to show lines of symmetry here, I can go like this. If I have a load applied on this horizontal member like that, this load P, the line of action of this load does not go through any of the lines of symmetry. There is even a distance between this line of symmetry and the load P. This distance is L. So this is a case of an eccentric loading. Now we can make this load eccentric. I'm sorry, concentric. By moving the load to a line parallel to its line of action, but going through the centroid or making it along the line of symmetry. So I can move the force P here, And as I move a force to keep it equivalent, then that would require adding a moment. So I can still get this P, but then add an M. And of course, this moment, M is going to be equal to P times L. Now, having a concentric load P is going to put a shear force in the fasteners that is going to be distributed evenly. So every fastener is going to get an equal share. So we can say here that, oh, there is a shear force getting into the fastener, and this shear force, of course, if P is acting downwards, each of these is going to get a component from P that is going to be like this. And I can refer to that as F1. And I can say that this F1 is equal to P divided by N, the number of bolts. So N here is the number of fasteners. But how about M? How is M gonna be taken care of? Imagine if this bending moment is trying to rotate one of the plates with respect to the other. The fasteners have to resist this motion. But if we're going to allow it to rotate a bit, if I know the centroid of this connection, which is here, this bending moment is trying to make this go. If I draw a perpendicular, this is going to try to move in this direction. This is going to try to move in this direction, and this is going to move in this direction, and this is going to move in this direction. So this is how the fasteners are trying to be sheared. Now, how much this relative displacement is going to be at the location of the fastener is going to be directly related to the amount of force that this fastener is going to have to take in order to resist the moment. And this distance is related to the distance from the centroid of the fasteners to the location of the fastener itself. So if I start to refer to this distance as R, so if I go like, I can call this like R1, R2, R3, R4. In an array of fasteners that is symmetric, or this kind of array here, we can see that they're going to be within, if this is like organized like a square, then they may be equal. But this may not always be the case. So the first step we want to find here is we need to find the centroid. We need to find the centroid of the bolt pattern. So need to find the centroid of the fasteners pattern. Now, this could be as simple as something like this, where I have plain lines of symmetry, and I'm done. I just use the geometry. Or if I do not have any lines of symmetry, then we can find the centroid location. Similar to what we did in statics, where we can use any convenient coordinates, and then I can come and say X bar is equal to the sum of AI times XI from I1 to N. So we're really taking the moments of the areas of the fasteners, each one of them. So I could have like N number of fasteners. In this case, we have 4. And I divide this by the total area of the fasteners. So I go sigma from I equal 1 to N of AI. And likewise, I can do a Y bar that is equal to sigma from I equal 1 to N of AI YI divided by sigma from I equal 1 to N of AI. Again, N is the number of fasteners, and I represent a particular fastener. AI would be the cross-sectional area of the fastener. XI and YI, they are coordinates of fasteners in a selected coordinate system. So how do we determine how much force each pin is going to feel? So each pin is going to get another component that is going to be resisting this moment. So as you see, this moment is trying to rotate the connection in the clockwise direction. So it's trying to push. I'm going to show here the components of the force that is trying to shear in the direction, as we show here, was given the relative rotation. So now I'm going to get here an F2 at fastener 1. I'm going to get here an F2 for fastener 2. I'm going to get here an F2 for fastener 3, and I'm going to get here an F2 for fastener 4. This F2 and I'm going to write it as the absolute value, is equal to, and by the way, likewise, this is the magnitude, right? It's the magnitude of the force. So this F2 is going to be equal to the moment multiplied by Ri divided by the sum of R J squared, and let me here specify this F2 sub I. You notice I wrote here F21, F22. So I'm going to call it here F2I. And it's MRI specifically divided by the sum of RJ squared from J equal 1 to N. Which, by the way, if we're looking at an eccentric force like this, I can also say that this is equal to P L Ri divided by sigma from J equal 1 to N of Rj squared. Now, once I get the F1 component and F2 component per fastener, we can easily find the resultant. And this would be the resultant shear force that each specific fastener has to handle. And of course, the most critical would be the one that has the highest magnitude in terms of shear force. Then we can start looking at the shear of the fastener. We can start looking at bearing, and we can start looking at the tear out. We can look at the tear out, and also we want to check for the member. Like a member like this is subject to a bending moment. And I should look at the critical section that has the most holes and calculate an equivalent moment of inertia and find the stress. I think the one thing that I didn't put here is R. And R would be the distance from the centroid to the fastener. And you can see it here where I wrote R1, R2, R3. And maybe I should specify that this is fastener 1, 2, 3, and 4. So this is kind of give us a summary of how we are going to approach shear joints with eccentric loading. Any questions so far? Okay, let's work out an example. So the example we want to work out is here we have in this figure, we have a 15 by 200. So I have here a 15. This is the thickness by 200 millimeter rectangular. So this is 200. And this is a rectangular steel bar cantilevered to a 250 millimeter steel channel using 4 tightly fitted bolts located at A, B, C, and D. So just by looking at this diagram, clearly we can construct 2 lines of symmetry for the array, and we can easily identify the centroid. So with this being said, I have no need to use these 2 equations to find X bar and Y bar. These 2 equations are going to be used if we do not have lines of symmetry. There is a force F of 16 kilonewton applied. So you can imagine like this rectangular steel bar is behaving like a cantilever. It's fixed to that channel, and there is a force that is being applied to it. And this force has a line of action that does not go through the line of symmetry or through the centroid of the pattern. We are asked to find the resultant load on each bolt, the maximum shear stress in each bolt, the maximum bearing stress, so that's going to be one number, and the critical bending stress in the bar. Critical bending stress in the bar. So if I consider here the centroid, point O is the centroid of the bolt group. And of course, we found this by symmetry. So using symmetry, we didn't have to use the equation. Now, if I sketch like a free body diagram and consider the cantilever like this, I have the force F equal to 16 kilonewton, and consider this as being fixed here. So if this is point O, then I would get, so this is like fixed, I would be looking at a reaction that has a shear force that is 16 kilonewton, and the distance to this point O, I'm looking here at the diagram, would be the 300 plus 50 plus 75. So I'm looking at 375 millimeters. I'm sorry, this is not correct. 350 and 75, this would be 425. Okay. So the shear force would be 16. And there is also a reaction to keep this in equilibrium. There is a moment reaction that is going to be equal to the 16 times the 425. So this is V equal to 16, and here M would be equal to 16 kilonewton. So this really should be 16,000. multiply by 0.425 meter, I will get 6,800 Newton meter. So that's the moment. So if I'm looking at the array here, I'm looking at A, the distance here is 60 and 75. So I will go here 75 and 60. This would be A. I would do the same here, 60 and 75. So this is B, C, and D. So this force or shear force of 16 kilonewton is going to be distributed evenly between the four. So I can come here and say, well, there is this F1 that is equal to 16 divided by 4 is equal to 4 kilonewtons. So each of these fasteners is going to see a 4 kilonewton going down like this. In order to find F2, we need to find the distance R. And this distance R is from the centroid to each of these fasteners. In this particular array, R happens to be the same for each and every one of them. So this is R, this is R, this is R, and this is R. Supposedly this should be like RA, RB, RC, and RD. So we can say that RA equals to RB equal to RC equal to RD. And they are all equal to the square root, if I'm using the geometry here, this distance here. This is 60, 60. And if we're looking here, 75 and 75. And of course, everything is in millimeters. So R is equal to the square root of 75 squared plus 60 squared, which is equal to 96 millimeter. Now, what is F2 equal to? F2, absolute value, is equal to MR, and this F2I, MRI, divided by the sum of RJ squared, from J equal 1 to N. But it happened that all the R's are the same. So that would make it this easy. I can say that the magnitude of F2 is equal to M R divided by the sum of the R's will be 4R squared. And I can simplify this. And then I do the math and say this is then equal to M divided by 4R. And again, this is for this particular connection. So this is not a formula to use for any type of connection. This is equal to 6,800 divided by 4 times this distance is 96 millimeters, right? So I can, this is a Newton meter. So if I do 96, this is like doing times 10 to the power 3. So I can do it here, 96 times 10 to the power 3 in Newton meter. And I will get here 17.7 times 10 to the power 3 Newton meter, or 17.7 kilo Newton. I'm sorry, there is no meter, sorry, kilonewton. So this is the F2 component. So we had the F1 that was 4 kilonewton, and I have the magnitude of the second force as 17.7. Okay, now I know the magnitude, but in which direction does this F2 force act? Perpendicular to the radial distance. Very correct. Very good. So I look here at A, and if I want to show the component, I'm going to be going, so this is 4, and this is going to be my F2. I come here at, let's say D, and I come perpendicular. So this moment is trying to rotate clockwise. Remember, this is the reaction moment. So this will be going, trying to rotate clockwise. It's going to be perpendicular. I get this here like this. I go to C, and again, perpendicular. I get this component like this. Come to B, and I get the component perpendicular like this. Now, the resultant shear is the sum of the F1 component and F2 component. How do we figure these out? We can do vector addition, or do the components, or use the parallelogram rule. I want to find the resultant force that is acting at each of these. If I look at, for example, these two forces, if I'm doing the parallelogram rule, if you recall, I'm going to draw a parallel and a parallel, and the resultant must be going, let me use a different color. The resultant is going to be going like this. If we do the same here, and here, what do you notice from using the parallelogram rule? These two parallelograms are alike, and these two are alike. And this is A and B. So I can say that the resultant shear force in A is equal to the resultant shear force in B. And if you apply the parallelogram rule, you can say between the 17.7 and the 4, I'm going to get 21 kilonewton. And RC and RD, so if I'm looking here, this is, let me put this, RA, RB, RD, and RC. So RA and RB are 21 kilonewton, and RC is equal to RD is equal to 14.8 kilonewton. So that's the magnitude of the resultant. Shear force. So now if I want to look at stresses, which fasteners are going to have the most critical shear stress? Must be A and B, right? So for part B here, we say that the bolts A and B are the critical with a shear force that is equal to 21 kilonewton. So when I'm looking at the shear stress in the bolt, I have to ask the question, is it going through the threaded portion or the unthreaded? So if I go back and look at what was given, if I look at this bolt that is being used, now this bolt length has to be more than 10 plus 15, which is 25, plus the height of the nut. And if we're using a washer, and then we also have to go 2 threads beyond that. So we can say the bolt height or bolt length is equal to 10 plus 15 plus, for the nut, we're going to put about 2 millimeters. No, 2 millimeters for a washer. And for the nut, we're going to look at the tables. If I look at, remember here, we are given that these are M16 by 2 bolts. So if I look for M16, I will find from table A31, I will find the nut height to be 14.8 millimeter. So this is for the nut. So I have 25 and 2 and 14.8. And then we also, so this is, we're looking about 40, yeah, we look about 41.8 here without the threads. Now we have, if I look at 2 threads, maybe we are looking at another 2 millimeters to have 2 threads outside. So we're looking at about 43.8 millimeters. No, actually, this is without 43.8 is the so I get 43.8 millimeters. So we say maybe we're gonna use a bolt of 46 millimeter. If I compute the threaded length LT using equation 814, I'll find that LT is equal to 38 millimeter. So the unthreaded length will be 46 minus 38. We'll find this to be 8 millimeter long. This 8 millimeter long is less than the 15 millimeter. So when you use that bolt, is not even the unthreaded portion or the threads are even getting into the first 15 millimeter plate. So we can conclude that this 8 millimeter is less than the thickness of the bar of the 15 millimeter. So the bolt will tend to shear across the threaded portion. If that's the case, then we have to use AD. And the AD in this case will be equal to 144 millimeters squared for an M16. So now we look at tau, the shear stress, and the shear stress is equal to the shear force V divided by the area. In this case, I'm going to be using the maximum shear force we just found, which is 21. So I will use 21 kilonewton, and I divide it by 144, and this is millimeter squared. So this is times 10 to the minus 6. We'll do the math here, and we'll find that this is equal to 146 times 10 to the power 6, or mega Pascal. Next, we want to look at bearing. So when I look at the bearing here, I have three components. I have the bolts, I have the bar, and I have the channel. And clearly, the channel has a thickness that is smaller than that of the bar. So the channel is thinner than the bar. So while it has to bear the same force, the area is smaller. So I can say that the largest bearing stress of course of the bolt pressing against the channel. So I'm going to take the sigma bearing, and we think of it as negative because it's pressing, is equal to this R max divided by the bearing area. And this maximum resultant that we find was the 21 kilonewton. I divided by the bearing area. And what is the bearing area going to be equal to? It's going to be equal to this 10 millimeter multiplied by 16. So these are in millimeters. So I can do times 10 to the minus 6. Or keep in mind that the answer here, I can raise it to the power 6. And I find here this is minus 131 131 times 10 to the power 6 Pascal, or sigma bearing is equal to minus 131 megapascal. Next, we want to look at the bending stress in the bar. Where is going to be the critical bending?
Right after the bolts farthest to the, or closest to the bolt.
So as the force is trying to get transmitted, bending, I'm gonna get like a critical section here, right? So if I'm looking at my bar, I have here, we have the force here, and then we have these bolts like this. So my critical section is going to be going through the holes. So we need to find the distance from the force to this critical section. I know the force is 16 kilonewton. And the distance would be the 300 plus the 50. So I have here 350 millimeter. And if we draw a free body diagram, I can find the bending moment right at this location. So this would be 16 times 350. That would be the critical bending moment. And this is 5,600. Okay, so this is resisting. 16 times 350, which is equal to 5,600 Newton meter. So this is M going through the critical section. Now, it is also important to understand what this critical section look like. So when I am cutting here through that section, this is what I see. The thickness is 15. And this is 200. And I have these two cuts. If this is the centroid, each of them is 16 millimeter and at a distance 60. Right? So the distance to the centroid of this is 60 millimeter. And each of these cuts is 16 millimeter. So this is my section. How do I find the bending stress? The bending stress, sigma, is equal to M over I times C. I know the moment, and C would be the distance furthest away from the neutral axis. Now, my neutral axis is here. So I know that this maximum distance C is equal to 100 millimeter. So how about I? Is the moment of inertia of this. How do I find the moment of inertia? Back to statics. We can do it by parts and use negative areas. So a moment of a rectangular is BH cubed over 12. So I can look at this. B is 15. H is in this case is 200 cubed over 12. So that's the moment of inertia of a rectangle. Then I use a minus to find the moment of inertia of these negative areas with respect to the centroid. So in order to do that, I'm using the parallel axis theorem, right? So I have two of them, and each of them is equally spaced from the neutral axis. So each of them has a moment of inertia of 15 times 16 cubed over 12. But they are not going through the centroid of the big section. So I add the area times the distance squared. And the area, the distance is 60 millimeter. So I have 60 squared multiplied by the area, which is 15 by 16. I close the bracket. So when I do the math here, I'll find that the moment of inertia I is equal to 8.26 times 10 to the power 6 millimeter to the power 4. So I solve for sigma, and sigma will be equal to this 5,600 multiplied by C, which is 100, divided by 8.26 times 10 to the power 6 Now this is in millimeter to the power 4. If I want to get the answer, so it's going to be in terms of millimeter. And I have 5,600, sorry, this is 5,600. 5,600 multiplied by 100. So we have millimeter divided by millimeter. So I have millimeter cubed. So to clear out the math, I multiply, if I multiply up here 10 to the minus 12 and 10 to the plus 3, this should be 10 to the power 9 to get it in Pascal. So I would get 67.8 times 10 to the power 6 pascals, which is then sigma is equal to 67.8 megapascal. That's going to be the bending stress in the plate. Any questions? Again, this is the summary of what we have done today. When we have a shear joint with an eccentric loading, we find the force that is going through the centroid and the moment. And the force is distributed evenly. The moment, each fastener is going to get a share depending on how far it is from the centroid. So it's function of the radial distance. And then we use, we look at the two components, F1 and F2, and add them together to find the resultant force that each fastener is going to get. Accordingly, we can find the shear stress in the fastener or the bolt, whether it's going through the threaded or unthreaded. We can find the bearing stress, and we can find the bending stress of the members as we have done in the example. This completes all the learning that we need to do in this class. I ask you to go back and complete homework 12, our last homework assignments, and start preparing for our third exam a week from today. It is going to be on this last section on bolts and fastener, everything that we've done, and you covered in homeworks 9, 10, 11, and 12. I already posted the model answers for homework 9 and 10, and we'll do the same for the others. So these can help you as you are studying. I've also posted the lecture videos on the modules. So if you want to go back to any of the things we covered in class, you have them. And basically, this coming Tuesday, we're not going to learn anything new, but I'll be happy to hold the class to answer questions and answers. Anything that you find out as you are studying, please bring it to the class. I'll be happy to address that in the class on Tuesday. All right. Have a great weekend, and I'll see you all on Tuesday. Thank you.